My name is Fergal Murphy from IGS. I'm going to talk to you about the Saudi Geological Survey Regional Geoscience project, and in particular the airborne geophysics. First of all, I'd like to acknowledge our partners, the Saudi Geological Survey, who are carrying out the work. IGS leads the technical partner consortium, and I acknowledge our other partners in that, and also want to acknowledge the airborne geophysical contractors who are acquiring the data, Excalibur and Standard Geophysics. Overview of my talk. I'm going to start with a little bit of background and the context in which this new project started. Talk briefly about the survey methods and the design, and I'm going to show some data examples and show how the data might be used. This is a bit of an overview. I'll go through it briefly. It just sets, it's a summary of the typical exploration process. On the left is where the role of governments come in delivering pre-competitive geoscience data. And on the right is the role of the larger mining companies at pre-feasibility, feasibility stage. SGS is carrying out this project in the context of supplying new pre-competitive data and hence stimulating exploration in Saudi Arabia. So the Regional Geological Survey program has three main components. There's airborne geophysics, geological mapping, and geochemical sampling. My colleague Jordan Gayoso from GTK is going to talk about the geochemistry later. I'm going to focus on the one on the left, the geophysics. Within the overall National Geoscience Initiative, which is part of Saudi Vision 2030, SGS is running this National Geoscience Initiative, and the RGP, Regional Geoscience Program, falls within this. And I spoke about the three components. There's also a National Geoscience Database, which all the data products from the three main data acquisition programs will feed through to. So getting to the geophysics, it's a very large project. It started back in Q4 of 2021. It's still in phase one, which is acquiring magnetic radiometry and radiometrics over the whole of the Arabian Shield. The map on the right shows the coverage to date, so it's about 80–85% complete. Block 1 in the northeast in blue has been completed by Standard Geophysics. They're currently flying a small extension, which is the bit sticking out on the east. Block 3 in the south and Block 2 in the northwest are being acquired by Excalibur. Block 3 is almost complete, and Block 2 is about 65% complete. The areas in red are exclusion zones, restricted zones for various reasons. They will not be covered. The whole project, phase 1, is 2.25 million line kilometers. Its scheduled acquisition and final products are scheduled to be complete by the middle of this year, and it's, to my knowledge, the largest single survey in the world. To date, over 2 million line kilometers have been acquired, 2 contractors, up to 9 aircraft deployed, and almost 12,000 hours of flying, and there's been almost 2,500 production flights. This sets the project in an international context. On the right is a map showing Saudi Arabia, and in particular the Arabian Shield in orange, on the same scale as Australia. Large countries with a strong mining history like Canada and Australia started acquiring airborne geophysical coverage back in the 1950s. Canada, for example, has not yet completed the whole country at 400-meter line spacing. Some recent examples, the Gola Craton in Australia has just finished back in 2019. That was 4 contractors, took 2.5 years, 1.7 million line kilometers. So you can see that it's a major achievement for Saudi Arabia to acquire a project of this size in just over 3 years. There's been some challenges. The weather in Saudi is very difficult for flying, lots of wind, dust, poor visibility, and also very rugged terrain over especially the western part of the Shield. But nevertheless, over 2 million kilometers have been acquired to date safely and to excellent technical specifications. Going back to old data over the shield, there was legacy airborne geophysics acquired starting in the early 1960s and complete by the early 1980s. This was acquired using the technology of the time. The line spacing was from 500 meters to 2 kilometers. The altitude was 150 to 300 meters, probably higher over areas of rugged terrain. The technology has advanced since this data was acquired, and it's no longer fit for purpose. So this is some of the reasons why we're acquiring new data. There was large technological improvements in airborne magnetics and radiometrics from the 1960s up to the 1990s. There have been minor incremental changes since then, but most of these changes date back to the 1980s and 90s. Primarily use of differential GPS for navigation and positioning, greater accuracy, recording rate and sensitivity of the magnetometry instruments, digital compensation for the magnetic effects of the aircraft, measuring horizontal gradients, such as this is an old image, but you can see the sensors on the wingtips and the tail. This helps to apply enhanced gridding and interpolation between lines. Digital data processing, greater emphasis on safety, and of course the final products are now all digital. So why magnetics and radiometrics? These are the standard methods for baseline geophysical surveying. They're relatively low cost per line kilometer compared to other methods. Relatively rapid to acquire. The systems can fly even through the Saudi Arabia summer. They're good for both structural mapping, particularly magnetics, and radiometrics, and magnetics in the case of lithological mapping. They can be flown on the same aircraft, and they meet the key objectives of this project, which is to acquire a set of baseline geophysical data to support the geological mapping project, and importantly, to stimulate exploration activity, and of course, to foster geoscience research and skills development in the kingdom. So all these advances in technology that we looked at enable much higher resolution magnetic and radiometric data to be acquired nowadays compared to the legacy data. So it's in this context that the project started. Just very briefly talking about the methods, the image on the top left is just a reminder about magnetics. The Earth's field is a dipole, so the magnetic anomaly that's measured depends on where one is on Earth, and typically one applies a transformation from the recorded data to a grid and then to what's called a reduced to the pole magnetic map, which makes it easier to interpret and focuses the anomalies over their causative source. The images on the bottom and the right refer to radiometrics. Radiometrics is only sensitive to the surface. The depth of penetration is only a few decimeters. And the assumption is that the gamma radiation emitted from the surface represents that the surface sediments represent the bedrock lithology. Of course, that's not always true, where we get transported eroded sediments. But typically over, especially the plutonic structures in the seal, we get very nice radiometric signatures that reflect the bedrock. A bit about survey design. So we choose a line spacing of 300 meters for the project with the tie lines. So that the main survey lines are running in the northern two blocks, running northeast, southwest. And in the south, running east-west. This is so the lines are running roughly orthogonal to the geological trends. As I mentioned, the systems are measuring gradient, which allow enhanced imaging and enhanced gridding, and gives better resolution data, especially offline. The data is suitable for interpretation at 1 to 100,000 scale, but it can actually be pushed down to about 1 to 20,000 scale. The survey height is 60 meters nominal, but of course where there's rugged topography, the pilots have to fly much higher than this. And some areas along the western escarpment, the radiometric data is missing because the plane was too far above the ground, and there are some gaps which were always expected. The airports are shown in red. As you can see, there's a limited distribution of airports, so sometimes the survey acquisition becomes quite tricky, and the pilots having to fly a long ways to get data. The line spacing is obviously a trade-off between cost and requirements, so the 300-meter spacing with radiometry measurement allows essentially one to replicate more or less what would be acquired with 200-meter line spacing and a single sensor. A bit about quality assurance, quality control. IGS and through the technical partner, we're hired by SGS to carry out independent quality control on the project. Just a reminder, a difference between quality assurance, which is essentially the written specifications. It's everything that goes into the contract. And subsequent memos to provide the clarifications. This is the reference benchmark on which the data will be evaluated. The quality control is the assessment of all the data produced by the contractors against these tolerances. And all of the data produced on the project has gone through quality control by the technical partner. The data products include grids, geotiff images, line database maps, and GIS packages. So far, some of the magnetic data grids have been loaded up to the National Geoscience portal. One can download these. The image on the bottom left is a screen capture of how the NGD portal looks. And you can get data for quite a few areas already. The image on the right shows what you will find on the portal by the end of this week. There will be a new data launch this week. Some of the data in gray and light blue in the bottom is still not absolutely final, but it's quite usable for interpretation purposes. The current geophysical data from the project is just the reduced to the pole rasters. One may request other data products from SGS via their portal. Just a quick note about if you decide to download the data, you should be careful to apply a suitable color scheme, a color stretch, and there's lots of different ways to look at the data, and not all software shows you the most suitable color schemes. I put as an example, a rather egregious example in the top right, typical rainbow color scheme, which is not what you want to use. On the bottom right is a perceptual color scheme, which this particular one is designed to show the large anomalies, both positive and negative. And the one on the right is a derivative, which is it's good to show in grayscale so you can see the detailed structure. So I'm now going to show some data examples. We're going to first of all look at the legacy data and compare the new data to see the uplift. In a lot of these examples, you will see structures such as intrusions, faults, dike swarms, folds. I'd like you to focus on the transition between slides. So this is the reduced to the pole legacy data. Subtle feature in the back is the first vertical derivative of that in grayscale. This is the first vertical derivative of the legacy data alone. This is obviously a big intrusion and a smaller intrusion to the left. And as we go to the new data, you can see the uplift compared to the old data. We start to pull out a lot more details. There's some nice structures coming through. You can see sinistral faults cutting the intrusion. You can see lots of detail in the contact aureole. Zonation within the intrusions. Obviously, there's lots of dike swarms. There's one cutting east, northeast, south, west, southwest here. There's another one northwest, southeast. There's a nice fold structure down here, and a subtle one here as well. And you can clearly see relative timing of structures from the offsets. And over on the far right, you can see how there's some sedimentary units being picked out, and there's some pinch outs. This is again just the RTP to see the amplitude of the magnetic data, so this helps us to identify which are the biggest anomalies, whereas the previous one kind of shows us the structure. This is the Sentinel-2 imagery false color composite for the same area. And then this is the radiometric data, a ternary image from the radiometric data that was acquired on the same project. So I'm going to see how these different data sets complement each other. You can see the white on this is where all of uranium, thorium, and potassium have high counts, and the black, like this image up here, is where all three have low counts. So typically the felsic intrusions will have high counts, but the radiometrics is quite useful for teasing out lithological variations, especially within the intrusive complexes. And this is the Peter Johnson 1 to 1 million geology map, and the structures on that are the 1 to 500K. So you can clearly see the benefit that will be added by this new data set, especially in mapping what's beneath the superficial cover, which was in blue in that last slide. And I'm now just showing some preliminary interpreted structures that have been generated by the contractor. Just added some false interpretations, very much a function of the time spent doing it, and obviously there's some more structures that could be picked out, but you have some false, mostly sinistral, and some dike swarms in red, and then there's some context in black, and it's a bit hard to see, but there's some lineaments and trends in blue. And this is a lithological interpretation generated by the contractor. As I said, interpretation is a function of the time spent. There's more detail that can be pulled out with more time. And next we'll move on to area 2. Again, I want you to focus on the transitions from slide to slide. So this is the legacy data. Again, we're looking at the RTP in color on top of the 1VD in grayscale. And the arrows in red show some of the mineral occurrence data. These are gold occurrences. These are all available publicly on the National Geoscience portal. We can see how the occurrences line up along the fault. And then moving to the new data, it's obviously showing a lot more detail again, and we can clearly understand how the what the relationship is between these mineral occurrences and the location of context and faults. And again, this is the geology map from Peter Johnson. And this is the 1 to 250K geology map, which was also compiled back in the, I think in the SGS BRGM days, and around the time that maybe it's been updated since. But this was mostly focused on the superficial cover. We can clearly see all the Neogean quaternary cover in the middle in yellow. And then we see how the magnetic data is really illuminating the buried structure and giving us new information. And a few slides, I'm going to show the area in red in a bit more detail. Again, I just want to note the difference. This is the contractor interpretation of the lithology and structures. Again, it's always going to be a work in progress. And this is the radiometric data for the same area. The large area in red are transported sediments, red indicating they're very high in potassium. This probably reflects their origin from some of the more felsic units. And the whole area on the left is relatively low counts, a lot of black, reflecting more mafic composition. And we can see how there's some like intrusions that have very high counts in white, and there's also some structures like this one here that look like an intrusion with very low counts. So we can see how the radiometric data is really helping to map the lithology. And again, this is the sentinel data, and again, sometimes it correlates with the radiometric, sometimes it tells us different information. So it's always good to look at all these data sets together and integrate them in carrying out any interpretation. So next, let's zoom into that red box. So I'm showing you this at what would be a 1 to 100,000 scale. And again, the same mineral occurrence data. We're looking here at what we call the first vertical derivative. So I typically use this product a lot for looking at the structure. But one can look at other higher order derivatives which show a little bit more detail. So if you're mapping structures in a lot of detail, you want to use all the different derivatives. Again, this is the second vertical derivative, so it's the derivative of the first derivative. And we see how there's more detail being pulled out. And again, I'm just overlaying the contractor-generated interpretation, but there's obviously a lot more detail that one can pull out of this. And this example here is what's called the tilt. And this is a very useful contact mapper. The areas in white reflect the location of contrast, i.e. magnetic differences in magnetic susceptibility across faults and lithological contexts, etc. So this is quite a useful product for locating edges. So in conclusion, so a new magnetic and radiometric data set has been acquired in just over 3 years. Acquisition is ongoing, but the acquisition will finish in the next few months. All data has been independently QC'd by the technical partner on behalf of SGS and meets rigorous modern-day standards. Initial data release on the NGD portal was the FMF last year. There was a subsequent release in October this year, and there will be more data released this week. The magnetic data is available for free. Currently it's available as reduced to the pole 1 to 100,000 map sheet tiles. The user may download these, stitch them together, and may calculate derivatives and enhancements using free and commercial software. Other data, grid database products, including radiometrics, may be requested from SGS via a form on the portal. The data is currently being used for the geological mapping of the Arabian Shield project, which is being done at 1 to 50,000 and compiled at 1 to 100,000. SGS very much encourages use of the data by private industry, universities, and researchers. There's obviously lots of potential for commercial and research uses over years and decades to come. Phase 2 and 3 of the geophysics project will commence in 2025, later this year, and will run for the next 3 years. And this will target the mineral belts and other target areas picked on the back of the phase 1 work. This will involve additional methods, including time domain, electromagnetics, gravity gradiometry, magnetotellurics, and probably also more higher resolution magnetic data in the target areas. For further information, you may contact Dr. Wadi Kashgari, who's sitting down here in front of me, who leads the RGB project. Also, engineer Mustafa Maki, who leads the NGD project, and Dr. Hussein Harbi, who is the RGB geophysics lead. And my contact on behalf of technical partner is there, and also the project manager of the technical partner, Dr. Esko Korkiakowski. And I'd like to thank you all for your attention and acknowledge our partners and SGS, and happy to take any questions. I believe we have lots of time, so I do have some more data to show if I'm allowed, but if I'll first take questions.
Thank you so much. I'm Ziad Al-Bashir from the Center for Industrial Revolution and CACS. It's obvious to us when you use the magnetic and you're imaging very well the structure, and even using the calculation of the derivative to see all elements that guide us to see the mineral depositions. But in terms the big picture that we need to see or increase the level of the confidence to see the minerals, what they exist over there. Are you going to use in future, or like pilot studying exist at each block to show the type of minerals that exist over there? This is one thing. The second, how about another technology? If we talk about hyperspectra, for example, or EM to look at as using as a satellite technology that may be fast and easiest way to empower the technology to increase the level of the confidence, because I think the final goal, how to show the big picture of the mineral reserves that exist in the Arabian Shield.
Yeah, for sure. Obviously, this project is just one piece in a larger jigsaw, and our main job is to ensure that this data set is fit for purpose. We're not the end users of the data set, so our core responsibility is to acquire this data on behalf of SGS and ensure that it's fit for purpose, so that other people can use it. And I know that SGS has plans to develop a data analytics center, and all these various data sets will be used in the future. And I didn't mention, but of course one can apply to this data and all sorts of edge detection and machine learning techniques, and one can integrate all the different data sets. You mentioned hyperspectral, for example. Satellite hyperspectral is being used as part of the geological mapping program. So, and along with this geophysics. So the mapping people are using hyperspectral, the geophysics, and the existing geological mapping data, the legacy data, to prepare preliminary field maps before they go out into the field to do the detailed mapping. And of course, this data can be used for target picking. But if there's phase 2 and 3, which will require new data at higher resolution and different types of geophysical data. I mentioned EM and magnetotellurics and gravity gradiometry. But of course, if a private company wants to do exploration in a particular area, they may decide to do their own survey work at a tighter line spacing on the back of this data set. For example, gold exploration people may want to do survey at 50-meter line spacing. Those faults I showed, obviously this data is really good, it's a big improvement, but it's probably not quite sufficient in itself if you're looking for structural gold. And obviously there's the geochemistry data as well. My colleague Jordan is going to speak later about that. There's 90,000 geochemical samples which have been taken over the whole of the Arabian Shield, so that provides a baseline data set for acquiring new geochemistry data. So it's very much about the integration of all the data sets. I'll just flick through a few extra slides just to show again the quality of the data. This is a whole intrusion complex showing here the RTP in a different color scheme, so you can see the amplitudes involved. Over on the far right there's a deep negative, which is an UFI light, a strong remnant magnetization there. This is the radiometric data, the ternary for the same area. Obviously some very high counts over the south. Some of the intrusions, some more of the intrusions of different characters. So the geology, again, this is a different area, a major sinistral system cutting through it, but lots of mafic units in this north-south running sinistrally displaced a shear, a fault zone. Again, this is the ternary for that area, and this is the geological map for that area. And yeah, that's just some nice pictures to show the diversity of the data. So yeah, thank you very much.